main topic for this cooling tower efficiency. Let's move in on to what we'll include for these lectures. So what is a cooling tower? So will be a quick recap, and then what is a range, and what is an approach. Number three, number four, what is a wearable and dryable temperatures, and then what's the design limit for cooling towers. And finally, we'll go to the calculations, which is the cooling tower efficiency. Okay. So what is a cooling tower? Moving on to this one. So you can see on the left side for the photo for cooling towers are used to remove the heat basically from the water using the water cool application industries. So this usually means removing the heat from water cool chillers. You can see a photo of the water cool chiller on the top right photos, and then the water cool chiller usually take the heat from the buildings. And you can see the common heat source at the bottom right of the photos. So you can know the heat source normally coming from the people, so ourselves, human beings, lights, plug load, and those are the electrical items plugged into the electrical outlet, and then the solar gain through the roofs, wall, and the windows. So cooling tower uses two mediums, that is water and air. So water bring the heat from the building and then use the ambient air around the cooling tower to absorb the heat and then take it away through the fan and then out to the ambient. So that's pretty much for the cooling towers. So let's move on to next. So what is the range? So the difference between the cooling tower uh, inlet temperatures, hot water temperature, and then cooling tower outlet temperature, which is the cold water air temperatures, is called the range of the cooling towers. So the range of the cooling tower equal to the cooling tower inlet temperatures minus cooling tower outlet temperatures. Or you can say that the range of the cooling tower equals to hot water temperatures minus the cold water temperatures. That's easier for me to understand. For examples, normally you have hot water coming to 5 degree Fahrenheit, and you have a cold water temperatures going out of cooling towers, maybe 85 degrees Fahrenheit. So that's easy to understand for most of the people. Uh, moving on to next. So what is the range? So this is another term using for cooling tower efficiency calculation. Is the approach. So basically, it's the difference between the cooling tower outlet temperatures, cold water temperatures, they called, and the ambient wearable temperature is called the approach of the cooling towers. So the approach represent a cooling tower capabilities basically. So, for example, sometimes during the summertime, you may lose this approach, um, as you might see. Okay. On the couple later, I'll explain to you. Um, so moving down to next, so let's talk about the wet bulb temperatures. WBT, this is very important concept. So wet bulb temperature is the lowest temperatures to which air can be cooled by the evaporation of the water into the air at a constant pressures. So we are trying to cooling the water by giving more air to take it out the heat from the waters. So that's a basic concept. And then the wet bulb temperature is measured by placing, for example, here you can see on the right side, placing a thin film of the water of the bowl of the thermometers. As you can see on the right side of the photo, out of two thermometer by uh, dipping a thin water layer around the bowl of the thermometers. Now the water layer present around this thermometer, and this temperature is called Weibull temperature. You can see it's a very uh, intuitive. Now you can see on the left side of the thermometers, this is a non-wet thermometer readings. provide the tribal temperature dBT readings. So there's no water there presenting around the thermometers. Now, another very important concept, now these two thermometers are at the same environment. So the difference is that one is with a thin layer of the water and another is without a thin layer of the water. As you can see, the difference in this in it's only in temperatures. So the wet bulb temperature is always lower than the dry bulb, except when the air is fully saturated with water. For example, a condition known as 100% relative humidity. At this condition, both wet bulb and dry bulb temperature are the same. So that's the only thing you need to remember is so when both are at 100% humidity, the temperature will be same for the dry bulb and wet bulb. Moving on to next slide here. So the design limit for the cooling towers. So this is the rule here. So a cooling tower cannot cool the hot process water to a temperature lower than the Weber temperature of the entering air. So basically, the the cooling water is impossible to cool hot process water lower than the Weber temperature of the entering air, because it is impossible to reject the heat to the atmosphere. Uh, for example, you have 90-degree um, coming in, you want an 80-degree, 85-degree going out of the cooling towers, and now your Weber temperature is 85. So you only can cool up to 85. If you want to cool up to 84, but your Weber is 85, then it's impossible. So as always, the heat is always flow from hot to cold. That's a basic principle for thermodynamics. And as a result, the lowest temperature of the water coming out of a cooling tower can only have the lowest temperature is equal to the Weber temperature. So that's pretty much the idea here. So let's move on to the next. For the calculation, this is very exciting now. For the cooling tower efficiency, as you can see this diagram, that's starting from the top, um, the right side of the diagram. So hot water coming in from the hot process water into a cooling towers. So at the middle, you can see this cold water temperatures going back to the process cooling waters. It's out of the cooling towers. And the difference between the top two hot waters and the cold water temperatures cold range. Now you can see the bottom side of the diagram, which is the approach. So cold water temperature minus the wet bulb temperatures. So cold water is the water coming out of the cooling towers, and the wet bulb temperature, which is the air coming inside the uh, cooling towers. So efficiencies you can see equals to the range temperatures over the uh, parenthesis of the range plus approach times 100%. So let's say 95 for your hot water temperature and 85 for your cold water temperatures. Now your wet bulb temperature in winter, for example, is 80, and in summer is 85. So you can see winter will be 60.6% for your cooling tower capacity, but summer you will have 100% because you are losing those approach. You can see here, approach is equal to 0. So in this case, you might have to have another cooling equipment such as evaporative cooling for your summer worst case scenario to account for that 100% cooling tower efficiency. So in practice, the cooling tower efficiency will need to be in between 70 to 75. Normally, you need to account for the summertime. So summertime, you want to keep those into 70 to 80, maybe 85-ish for those. So the ambient air Weber temperature raise in the summertime compared with the winter time. So cooling efficiency limiting in the summertime is very common. So since you can see the only factor that is changing around For this calculation, it's the wearable temperature. So once that increase, for example, in extreme case, you might have a zero at the approach, which will make the efficiency equal to zero, 100% for your calculations. As you can see, it's range over range, so that's 100%. It's automatically. So which means you cannot remove more heat. So if you're running into this kind of question, you have to have another cooling equipment such as another evaporator cooling system or to have more coolants. I hope you enjoyed these videos. I really enjoyed this topic and I would like to talk more with you for other topics later on. And thank you so much for watching. I'll see you in the next one.